Hi everyone, I'm Won Lee. Today's topic, section 6, 1 minus alpha 100% confidence interval for population proportion P. It is very much similar with confidence interval for population mean mu. That's why I said statistics is simple, easy to understand if you understand the basis. I mean, 1 minus alpha 100% confidence interval for mean mu is the basis. Okay. All right. Let's see. Oh, by the way, I left a little uh, about t distribution here. T distribution table. Okay. This table will be provided at your textbook, statistics textbook. All right. If but if you analyze the data using a computer program will provide accurately calculated probability from the distribution function f of t for random variable t. This is, just a brief, a simple table because t table shown at the left contains t value. These are now t values, okay? Value of t. For different degrees of freedom, T distribution has degrees of freedom 1 to up to infinity. Okay, and some corresponding to various probabilities in the right tail here. This one. When this one is 0.0005, the t value degrees of freedom here, t value will be here. There's a freedom 5, then 6.869, something like that. So t distribution table, okay. What is the noteworthy in this table is that when the degrees of freedom are infinity, okay, what happened? Standard normal distribution G here 1.96 is what? 0.025. I mentioned it is a famous value of G, okay, 0.025. So 0.025, well, here. So degrees of freedom increases up to infinity. It is the value of t is 1.96, same thing. So t value corresponding to the area 0.025 in the right tail is 1.96. This is the same as value for 1.96 in the standard normal distribution table, where the area in the right tail is also 0.025. It indicates that as degrees of freedom for t distributed random variable t increase, degrees of freedom increase, the t distribution approaches the standard normal distribution. Okay, it can be proved theoretically. And let's take a simple example here. Okay, suppose we obtain data on number of customers served by a particular employee at a service counter over a period of 10 days. 10 days number of customers served, okay? So 172 to 170. It is assumed that number of customers served by the employee in a day follows a normal distribution because the sample size is only 10. So I like to assume this data, okay, this data follows a normal distribution because T comes from normal distribution. What? X bar minus mu S square root to N, okay? So estimate the average number of customer mu served by this employee in a day is sample mean 171.7. Standard deviation of data above is as 2.452. Calculate 95 confidence interval for mean mu. Then x bar, this one, 171.7 times t value. What is t value? T value is now degrees of freedom 9 and 0.05, 025, then 2.262. 2.262 times S 2.452 divided by square root n 10. Okay? And the same thing plus here. And how about the 90% confidence interval for mean mu? Then this value, t value, just change change to what? Here, 90%. So one side is what? Oh, 90%. So one side is 0.05, right? So 1.833 come here. In result, the width of this interval is what? Shorter than this interval. 95 confidence interval, confidence interval. Okay? All right. Let's see. Today's topic, confidence interval for proportion P. Having dealt with the estimation of a population mean mu, let us now address estimation of a population proportion P. The population proportion can refer to defect rate, voter support rate, customer market share, default rate, pass rate, and so on. There are many proportion data. The best estimator for population proportion, P, is the sample proportion obtained from the sample, denoted by P hat. We studied it, chapter 3. The concept of a population arises from the Bernoulli distribution, specifically when the population is described by population. Okay, x equal to 1 if success, x equal to 0 if failure, and probability of x equal to 1 is small p. This is population proportion. It becomes a matter of estimating p. It is also essential to obtain a sample in this case, okay, from the sample x1, x2, xn. x1 takes 1, 0, x2 takes 1, 0, xn takes 1, 0. So sample mean x bar is what? X bar is number of ones here divided by, let x divided by number of sample n, right? x1 plus x2 plus xn means the number of successes. So that is a sample proportion p hat. P hat is x bar, x1, x2, xn divided by n. That is the best estimator for p. We studied the distribution of a best estimator p hat. Okay, according to central limit theorem, p hat has normal distribution with mean p, variance p 1 minus p over n. We also studied it, chapter 3. Therefore, confidence interval for p at 1 minus alpha 100% confidence level is what? P hat minus g alpha over 2 times this one, square root of this. What is this? What is this? We call it what? Standard error of p hat, because p hat is a statistic. Statistics standard deviation is called standard error. It is a standard error, all right? Same value here. Hence, since we do not know the standard error of p hat, we do not know this value, okay? This value, because we do not know p, so we do not know standard error of p hat, this one. We have no choice but to use its estimator is like this. Just the substitute p hat instead of p here. Ultimately, the confidence interval for p at 1 minus alpha 100% confidence level is like this. So it is very coincide in the process. Your logic is same as population mean. When we studied population mean, there is no difference. Of course, there are some differences like p hat, okay, distribution of a p hat, but the logic is just the same. Okay, okay. Somebody, this one, p minus p hat from here, divided by square root p 1 minus p over n. It is standard normal. But when we substitute p hat, oh, it's going to be different random variable and something like t, no way. Okay, it is what? Mystery. The distribution of p 1 minus p hat over square root p hat times 1 minus p hat over n, it is not, the distribution of this part is not found yet. So you don't have to worry about, but if somebody is interested in this one, distribution of this part, then you better forget it. Okay? Thank you. Bye.